Hello there, bright minds. Ever wonder how your makeup mirror or a shiny spoon bends the world you see? Today, we are diving into the fascinating world of spherical mirrors, those tiny slices of spheres that create magic with light. And here's a quick joke to get us started. Why did the concave mirror break up with the convex mirror? Because it found the relationship too reflective. Alright, jokes aside, let's get serious about these mirrors. Spherical mirrors are parts of a sphere's surface and they come in two flavors: concave, which curve inward like a cave, and convex, bulging outward like the back of a spoon. When light hits these mirrors, it follows the law of reflection, which simply means the angle at which light arrives equals the angle it bounces off. Angle of incidence equals angle of reflection. Now, picture the mirror's pole, marked as P, right at the center of the mirror's surface. Then there's the center of curvature, C, which is the center point of the full sphere from which our mirror segment originated. Imagine a straight line passing through P and C. This is the principal axis. Halfway between P and C lies the principal focus, denoted F, where light rays tend to converge or appear to diverge. The distance between P and C is the radius of curvature, symbolized by R, and the focal length F, which is the distance from P to F, is always half of R. So, focal length F equals radius of curvature are divided by 2. We also use a sign convention for directions and distances based on the mirror formula rules. The nature of the image formed by a mirror depends on the position of the object relative to the focal point, F, and the center of curvature, C. Depending on where the object is placed, the image may be real or virtual, inverted or upright, and magnified or reduced. The standard ray rules are as follows. A ray parallel to the axis reflects through the focus. A ray passing through the center of curvature reflects back on itself. And a ray passing through the focus reflects parallel to the axis. For convex mirrors, however, the image is always virtual, upright, and diminished. It always appears behind the mirror, no matter where the object is placed. Magnification is given by the formula m equals h prime over h, which is equal to negative v over u. Magnification is negative for real inverted images and positive for virtual upright images. Alright, time to put on our thinking caps and understand the math behind those reflections. The mirror equation isn't just a random formula, it's firmly rooted in geometry. Using similar triangles formed by the object, image, and reflected rays, and assuming rays are paraxial, that is, very close to the principal axis, we derive the relation 1 over image distance plus 1 over object distance equals 1 over focal length. Let me say it in words again. 1 divided by v plus 1 divided by u equals 1 divided by f, where u is the object distance, v the image distance, and f the focal length. Now, the sign convention here follows Cartesian rules with a special twist. All distances are measured from the mirror's pole P. Distances measured in the direction of the incoming light toward the mirror are negative, while heights above the principal axis are positive. For example, the object distance u is normally negative because the real object is placed in front of the mirror against the direction of the incident light. For concave mirrors, the focal length f is negative. For convex mirrors, f is positive. Image distances v and their signs tell us where the image forms, if it's in front or behind the mirror. In concave mirrors, a real image means v is negative, and for convex mirrors, since images are virtual and behind the mirror, v is positive. The diagram illustrates this derivation beautifully, showing two triangles formed by object ab and image a prime b prime, labeling all the distances u, v, and f along the principal axis, helping us see how geometry guides the mirror equation. These sign conventions might look like rules, but they ensure that calculations match real-world physics perfectly, which is crucial when designing optical devices like cameras and projectors. Let's solve a concrete example to see how this all comes together in practice. Suppose we have a concave mirror with a focal length of -20 cm. Remember, for concave mirrors, focal length f is negative. An object is placed 30 cm in front of the mirror, so object distance u is -30 cm. Our goal? To find the image distance v and the magnification m. Starting with the mirror formula, 1 over v plus 1 over u equals 1 over f rearranged, 1 over v equals 1 over f minus 1 over u. Plug in the numbers. 1 over v equals 1 divided by -20 minus 1 divided by -30, that is, -1/20 plus 1/30. Finding common denominators, that's -3 over 60 plus 2 over 60, which simplifies to -1 over 60. Wait, double check. Actually, -1/20 is -3 over 60 and 1/30 is 2 over 60, so -3 plus 2 is -1, so 1 over v equals -1/60, meaning v equals -60 centimeters. Hold on, a negative image distance means the image forms on the same side as the object, which is in front of the mirror. This suggests a real image 60 centimeters in front, twice the object distance, confirming it's magnified. To find magnification, m equals -v divided by u, that's -60 divided by -30 equals 2. That means the image is real, inverted, and magnified 2 times. Looking at the ray diagram, the image appears beyond the center of curvature, bigger and upside down compared to the object, just as our math predicted. This example shows how formulas and sign conventions decode real-world image formation, whether it's for a shining torch reflector or a dentist's mirror. Time to wrap up our exciting journey through spherical mirrors. We learned that the mirror equation basically says 1 over the image distance plus 1 over the object distance equals 1 over the focal length, your all-purpose optical key. Magnification is the ratio of image height to object height, which also equals negative image distance divided by object distance. Negative values mean real and inverted images, and positive values mean virtual and upright. Remember, the focal length is simply half the radius of curvature, so f equals are divided by 2. Concave mirrors are versatile. They form real inverted or virtual upright images depending on where the object is placed. On the other hand, convex mirrors are the modest ones, always producing virtual, upright, and smaller images no matter what. And a special shout out to sign conventions, the unsung heroes that keep our calculations in check and consistent. So whether it's in makeup mirrors, vehicle side mirrors, or optical instruments, spherical mirrors help us see our world in amazing ways. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.